most of you who came here already know the project. So that is why I've been talking so quick, so fast. And I want to just go through this part quickly. And the next thing I want to introduce is actually the main topic of our code camp, which is a consensus algorithm. And after that, I will introduce the coding part, just how to develop on Algorand. And after this session, there will be a session break of 10 minutes. And I think we will have enough time to cover this in about 30 to 40 minutes. And then we will have a 10-minute session break. And then we will move on to the coding part, which I will spend more time on this. Okay, let me start with this consensus algorithm. So in the last session, I was introducing Algorand as a project, but for your information, Algorand actually stands for two meanings. It's the name of two things. Algorand is first the project, the name of the project, of course, but also it is also a name of the consensus algorithm that is supporting the project. So the Algorand consensus algorithm was developed by Professor Silvio Micali, the Turing Award winner, and his student Jing Chen. And the story happened in a cafe in the MIT campus, campus cafe, and they were discussing about this problem, and they got this idea on a new consensus algorithm, and then they get back to their lab and finish this paper and submitted it. And the paper was accepted at a conference named SOSP, which is a top conference in the computer science field. And after that, after the paper was accepted, and they started to try to build a startup around this new consensus algorithm to build a product, the Algorand blockchain platform around this consensus algorithm, and to adopt more business applications, more use cases onto this platform. And thus we have derived the Algorand Inc. and Algorand Foundation, and we are working on the ecosystem of this project, and also a lot of things, developer community, and we had grown very big. So the reason I want to introduce the consensus algorithm is obvious, which is that the consensus algorithm is actually the core of the whole tech stack of Algorand. So this is the part that makes the whole system secure. And this is the part that influences the overall efficiency of the whole system. So if you don't get this part right, then anything you build on the platform, any applications, any smart contract you build on it will be fundamentally failed. So it's very important to understand this part. And I will start with a little bit background knowledge of what is consensus algorithm. So here on the screen, you can see there's a lot of different consensus algorithm here. I'm making the quoting gesture here. So consensus algorithm, so a lot of people claim that they have developed a consensus algorithm and they name it after proof of something. For example, proof of time, proof of what's R. I don't know what it is, but this is actually a huge misunderstanding in the crypto space, as that all of the things you see on this screen are actually not consensus algorithm. So I will explain why these are not consensus algorithm, and I will explain what is consensus algorithm by definition. So I will start with a little bit background knowledge, and I will just get into a little bit details about what is network assumption and security assumption of the consensus algorithm, and I will introduce several classic consensus algorithms. And this part I will include the Algorand. So the background knowledge. The consensus algorithm, this academic category actually came from the distributed system field. And this is actually also a subcategory under the computer science field. And a distributed system is actually pretty common. Take the example that you take a flight from one place to another. It is the distributed system in the plane that keeps you safe and keep your plane functional. And a distributed system is actually just a bunch of computers that talks to each other. They send messages to each other, and they work with each other to make as a whole system, and to make the whole system work functional. And as the plane is actually a good example, as it definitely has multiple computers, and they are connected with each other through hardware, hardware cable. But you can also consider our network to be a distributed system, as they are also talking with each other, but only through sometimes through the wireless communication, sometimes the wired communication. And in a distributed system, you can abstract the whole architecture like this. So you have a multiple node, and by node, I actually mean that each node is an independent computer, and they talk with each other through some kind of message protocol. And you, as a client, you can send a message to this distributed system, and in hope of getting some response from it. Maybe you can send a computation request to the system, and hope that it can get back to you the result of your computation request. And so this is a concept of the distributed system, and we will see this architecture a lot in the following session. And also another concept that I want to introduce is the state machine. So what is a state machine? Generally speaking, a computer is already a state machine. So here inside of this basket, you can see there's a multiple state, from initial state to state 1 to state 2 and to state n. And the transition between each of the states happens when there's an outside input or event, right? So let's say that at first we have an initial state, which is, let's just take the example of blockchain. Let's say we have an account on blockchain, account Alice maybe, and the balance of the Alice account is 0, and this balance is 0 can be considered as an initial state. And if you send a transaction into this state machine as an input, as an event, then there will be a state transition from the initial state to state 1. So maybe you send a transaction to the Alice account with an amount of 100, and the initial state will be Alice account has 0, and the state 1 will be her account has a balance of 100. So this is kind of the concept of state machine. It has multiple states, and there's a state transitions between each state when there's an input and an event. And based on that, we have another concept named the replicated state machine. So what is a replicated state machine? It's basically just replicated the state machine. So we have a state machine, and you just take a replication of it. And we have things like this because we want to make sure that we have different computers, different nodes globally, and they all have the same data about a single system. They want to make sure that they have the same output to the outside input whenever they are trying to execute this input request. So we want to make sure that all of the states, the final state of these different nodes are the same. And here is actually what the consensus algorithm do. It helps to make sure that the final state stored in each of these nodes are the same, even though that they are totally independent computers. They do the computation based on themselves, and the only thing they do together is that they have a communication protocol between them, and they can talk to each other to receive messages from each other, and the consensus algorithm make sure that they have the same final state. So the definition of a consensus algorithm actually contains also two concepts. One is called agreement, or you can call it consistency, and the other one is termination, or you can call it levelness. So agreement means that in a network like this, in a distributed network where you have multiple nodes, and each node is a state machine, and you have a replicated state machine network. Agreement means that all the non-error nodes can agree on a sequence of events and generate the same output. Agree on a sequence of events means that you will receive a sequence of events from the outside, and each of the nodes will also all of them will receive the same transactions from the outside, but they probably, due to the network error or some delay, they might receive these transactions in different orders, or they might miss some of the transactions. So the agreement here means that we want to make sure that all the nodes that has no errors can agree, can indeed receive all the transactions, and they can receive all the transactions in the same sequence, so that once they have the same sequence and they also have the initial state, you can see that they will have the same final state, right? Because the state transition is based on the last state, and as long as you have the initial state correct and all the transaction sequence correct, and you will have the final state correct. And another property is called termination. So we want to make sure that all the non-error nodes can generate an output under a certain time. So this is because that there are cases that you send a transaction to this network, and you wait for maybe a year or 2 years for, and they still are not getting back to you on the response, because they said they are still working on getting the right sequence of the transaction. They're still working on this property, but they forgot to, they need to like a lot of time to terminate to get the final result. So we also want this property. So combining these two property, we can try to define the consensus algorithm, which can fundamentally support these two properties. And also we need to face 3 challenges when designing a consensus algorithm. First is that we don't have a global consistent clock. So the reason we have a global consistent clock is pretty important, is that just consider the agreement property. If you want to receive, want all the nodes to receive the same sequence of events in events, then the easiest thing you can do is to attach a timestamp on each of the events or transactions. And so that when each node here receive the event, they can just say what is the timestamp on this transaction, and they can just order all the transactions in order of the timestamp. But the problem with this approach is that there's no global consistent clock, which means that you cannot find a clock that tells each of the nodes the exact same time at the same time. Because even though you can place a clock somewhere in this world, maybe let's say you place it in Singapore, you have clocks in Singapore, and you let all the nodes globally to send a request to this clock to ask for the time, there will be a time delay when they're transferring this request message. And then when the time that the message gets to this clock and the response gets back to the node, there will be a huge message delay, and which makes the timestamp, the time they received, are different. So this is actually an academic proved conclusion that there's no global consistent clock. And another thing is that each of the node could fail independently. So this is also an important property, as that we know each of the node, they could, because they are distributed globally, they are in different places, and there might be a powerage outage. There might be a just a hardware malfunctioning, which makes the node fail. And we need to also take this into consideration when designing a consensus algorithm. And also the messages transferred in the network are not always reliable, which means that the message can be delayed, can be missed, or can be, just misplaced, misunderstood. All of this could happen. So taking all these 3 challenges into consideration, we can have a definition of consensus algorithm, which is that it is a protocol that makes all non-error nodes in a replicated state machine network to first agree on the sequence of transactions, which is agreement property, and second, to generate output in under a certain time, which is a property of termination. And also it needs to face these 3 challenges. So here is the definition of consensus algorithm. And after we learn about this consensus algorithm, we need to understand another theory, very important theory. So in order to design a consensus algorithm, the first thing you need to know is what is impossible. And this is defined by the FLP impossibility theory. It is a paper published by Leslie Lamport, and it's a mathematically proved paper that give us a very very important conclusion, which is that so this is a original word I quote from the paper. So in synchronous network where messages may be delayed but not lost, so there is no consensus algorithm that is guaranteed to terminate in every execution for all starting conditions if at least one node may fail stop. So if there's, so just to understand this FLP impossibility and to rephrase that, you can say, put a simple way, that a consensus algorithm to design a consensus algorithm, you can either choose a synchronous network assumption or termination. So as we mentioned, a consensus algorithm needs to meet two properties. One is termination, another one is agreement. But here, as you can see, that we cannot have the termination and also this thing, a synchronous network assumption at the same time. So in another word, you need to choose between this. And in order to design consensus algorithm, you need to do trade-off between these two properties. And the first very well-known consensus algorithm proposed was Paxos. This is still a very popular consensus algorithm that is used in a lot of the distributed nowadays. Maybe I think Google or Amazon's AWS are still using things like this to keep their server running, keep their distributed system running. And this is a good example that it adopts synchronous network assumption to achieve consensus. So as you can see here, you can choose only these two properties. So in the case of Paxos, it chooses to have termination over the asynchronous network assumption, and it adopts a synchronous network assumption. But it seems that we have solved the problem of the consensus algorithm so far, but there's another challenge we are facing in the case of blockchain. So so the Paxos is used, as I said, in maybe Google Cloud or AWS, but the environment in the Google Cloud is that you may have computers, you may have nodes that fail because of non-human reason. But in the case of blockchain, you could have nodes that fail you on purpose. And this is a theory we call Byzantine fault tolerance. So in this environment, you could have nodes that fail you on purpose, that maybe it delays the message response on purpose. Maybe it sends you the wrong message response. Maybe it alters the message that it's received or it's sent. And just by any means, they are trying to jeopardize the whole system. And they are usually coordinated. So all the attackers work with each other to make the whole system fail. And they are doing this on purpose. So this is called Byzantine fault tolerance situation. And before we talk about how do we solve this this problem, this further problem in the context of blockchain, we need to explain a little bit about the network assumption and the security assumption. So I mentioned here a synchronous network assumption and also a synchronous network assumption, but you may wondering what is it actually. So here I can introduce this a little bit in detail. To design a consensus algorithm, we can, as the FLP impossibility theory suggested, we can either have termination or asynchronous network assumption. So in order to design a functional consensus algorithm, usually the approach would be to make some network model assumption inside of the consensus algorithm to make it mathematically proved. And here are three kinds of the models that we usually use to achieve this. So a synchronous model means that in this network environment, message can be delayed indefinitely. So a message you send could be received, will be received by the recipient, but you have no idea when the recipient will receive it. It maybe take 10 years, a decade, 100 years, a century. it could be possible, but you cannot make an assumption that the message will be, you can make the assumption that the message will be received, but you cannot make the assumption on when it will be received. So this is called a synchronous model. And a synchronous model means that the message will be received and it will be received in a certain time. So you have a certain time delay that you know, maybe like 10 seconds or 10 minutes, that you know that in 10 minutes, the recipient will definitely receive the message from me. So this is called synchronous model. And also we have the partial asynchronous model, which is kind of the combination of the first two kinds. And under this model, it assumes that the network is synchronous on a good day. So it assumes that there is a good day and there is a bad day. On a good day, the network is synchronous, which means that all the message will be received under a certain time. And on bad day, there is a synchronous. The situation is synchronous, which means that the message can be delayed indefinitely. So a good day and bad day is actually just a phrase that is used in the context of the network. So it basically means that you need to handle all of these situations in the consensus algorithm design. And also another part that I need to emphasize is the security assumption. For most of the consensus algorithm I'm going to introduce, there is a security threshold, which is this. The n here is the number of the total nodes, the total number of the nodes, and f here is the number of the Byzantine fault node. So in order to make any consensus algorithm work, and that applies to all of the consensus algorithm here, PBFT, Tendermint, and also Hausdorff Algorand, we need to make sure that the total number of the nodes is no less than 3f plus 1, and the 5f is the number of Byzantine fault node. So basically no more than 1/3 of the Byzantine fault node. And this applies to all of these consensus algorithm, and especially the quorum-based consensus algorithm. I'll explain what is this. So here I will introduce Algorand consensus algorithm and a couple of other classic examples. The first one is PBFT. So here's a diagram that shows how PBFT works. So here the C here is the client, and here from P0 to B1, B2, B6, these are some of the nodes. And in order to use this system, the client needs to first send a request to one of the nodes in this distributed system, and then you can also consider this as a blockchain. So all of these nodes are the nodes of blockchain. So as a client, as a user or developer, you need to send a transaction, a request to one of the nodes in the blockchain. And then this node will propose this message to all of the other nodes at this round, and then all the other nodes will propose the other node, the request to the other node to vote on it. And at the round you will have 1 vote, and this round you will have 2 votes. So at each round of voting, you need to reach a quorum to get approved on this message. And usually this involves more than 2/3 of the votes from the committee. So out of the nodes, there's 6 nodes. If there's 6 nodes here, then you have at least 4 votes on a single message, on a single transaction, and says that this is valid to make this round of consensus valid. And at last, you just send the response back to the client. So this is how PBFT works. And the slides will be available. I will send the slides afterwards in the Telegram chat. And so what's special about PBFT is that it's actually the first, maybe not the first, but the most well-known consensus algorithm that's make use of the partial synchronous model here. And also Tendermint. Tendermint is, as you can see here, it's what's special about Tendermint is that it has a loop. So as I mentioned that in the partial synchronous model, you need to handle both a good day or a bad day. And this is in a PBFT diagram. What you see here is actually the good day situation. So all the message will not be delayed indefinitely. They will be received under a certain time. But if it's a bad day where the message are delayed indefinitely and beyond the threshold that you predetermined, then what you need to do is to do something called a veil change, which is also a part of the consensus algorithm that handles this kind of situation. But in the case of Tendermint, you can say that there's no mechanism that help you to handle the veil change situation, the bad day situation. What it does is that it has a loop. It just go through this loop round and round, and just until you have the consensus reached. And another one is called Hotstuff. So this is kind of the so the Hotstuff is actually the algorithm used in Libra. It's developed by a good friend named Ted, and he's now at another project called Ava. And the Hotstuff is actually, I think, in my personal opinion, is very how should I say? It's very elegant consensus algorithm, and it abstracts all the complexity from all the previous consensus algorithm and make it very simple and very secure. So this is basically, I think, the best consensus algorithm in terms of the this kind of quorum based consensus. And here's can algorithm on a mobile phone. I think our consensusism is doesn't require a lot of hardware specifications, and we have a case that we can run an algorithm node on a Raspberry Pi, and I think Raspberry Pi is much low demanding than a mobile phone. But the problem is that we don't have a software that supports that supports running the node on a mobile phone right now. But it is possible. I can say that the protocol level supports that, but we just don't have the software yet. But on a Raspberry Pi, I think it's okay. So here I want to give a quick conclusion to all the summary to all the previous solutions. Proof of work based algorithms, for example, Nakamoto consensus, and also quorum based algorithms such as PBFT, Tendermint, and Hotstuff. So they all have their advantages and they all have their drawbacks. For example, proof of work has fork, which means that you need to wait for more than one block to get your transaction to be confirmed, and which also makes the finality slow, the transaction finality slow, as you need to wait for, in the case of Bitcoin, 6 blocks to get your transaction confirmed. And on the other hand, if you are using a quorum-based consensus algorithm like PBFT or Hotstuff, then there will be no fork, and every transaction can be confirmed in a single block, which makes the finality very fast, transaction finality very fast. But the problem with this quorum-based algorithm is that they have very limited decentralization, which means that they can only have around 4 to 100 nodes in the network, and which usually makes the whole network permission, that you cannot have a permissionless network, as you can only contain less than 100 nodes in the network. And but in the case of POW proof of work, you can have limitless number of nodes, and you will have the permissionless property, and you can welcome all the nodes to join your network. So this is a comparison between these two kinds of consensus algorithm, the proof of work Manning based and quorum based. So here I want to give a very quick high level explanation to Algorand, and then I will introduce the process of Algorand in detail. So first we use a pure proof of stake mechanism as the node permission mechanism. So here is to echo the thing I said in the first slide, that proof of stake is actually not consensus algorithm. It is only a node permission mechanism that stops you from getting nodes into the network to participate into the consensus. And the reason we need to design things like that is because we have the security assumption that I mentioned in a previous slide, that in order to make a consensus algorithm functional, we need to we need to make sure that no more than 1/3 of the nodes are presenting false nodes, and that assumption doesn't exist in a blockchain system generally. And to make that environment for the blockchain, we need to have a node permission mechanism, and this actually usually involves some incentives to make them a stakeholder and to make them less incentivized to be a presenting node. And and in the case of Algorand, we adopt a pure proof of stake mechanism. Okay, so the reason that they have limited nodes is that, maybe just let's take an example of this. As you can see, in the case of PBFT, you need to have the message to be broadcasted to each of the nodes twice, right? And the limitation on this is the bandwidth. So in order to broadcast, as you can see, from this node to all the other node, broadcasting a message to others broadcasted once takes a part of the bandwidth, and broadcasted twice takes two parts of it, twice of that. And if you have 10 nodes, then you need to send it 10 times. If you have 100 nodes, then you need to send it 100 times. And also considering the network delay in the whole network, you will see that because of each of the nodes, they have different bandwidths and they have different network situation, the whole overall efficiency of the network will be delayed when the number of nodes increase. So this is because, as you mentioned, the reason because we have the limited nodes here is that we don't want to have too many nodes in the network to send each other to send each other on the we don't want to have too many nodes in the network to send each other messages, to take too much bandwidth, and so this is the main problem. In replace, we can all follow change replace. So yeah, I was talking about the pure proof of stake. So comparing to the existing proof of stake mechanisms, it has we don't require any tokens to be locked up, and you can just hold your tokens on your account, and you will be able to participate into the consensus in proportional to the tokens you have. And there will be no punishment, just one token stands for one piece of voting power. If you have more tokens, then you have more right to participate into the consensus. Yeah, it can be more than 100 nodes, but it will be much slower. And this is mainly limited by bandwidth. And as you suggested that maybe 5G will make this better, but I believe it only solves a part of the problem. Let's say 5G increase the bandwidth for 20%, maybe 20%. I think 20% is a big number already. And then the improve on the node number is from 100 to 120, which is not a significant difference compared to the limitless number of nodes in a proof of work system, which I think has more than 1,000 nodes at the current time. And we have two phases. So as I mentioned, pure proof of stake is merely the node permission mechanism that controls what kind of node and how many nodes can actually participate into the consensus algorithm, and this is for make sure that the environment of the consensus protocol meets with the security assumption that no more than 1/3 of the nodes are presenting node. And after you go through this mechanism, you can then participate into the consensus protocol, which has two steps. The first step is that we will involve a function called VRF, verified random function. And this is a function that you can run offline on your local computer. And you can consider this as basically a drawing a lottery. and you can, and you are doing this secretly. Nobody will know what lottery you draw until you show it to others. And you will be able to draw a lottery to know that if you can participate into the actual consensus process, and the probability of getting the lottery is in proportion to the token you have. So if you have 100 tokens, then you have 100 pieces of probability to join the consensus in this round. And if you have maybe 1 million tokens, then you have more possibility to join the consensus in this round. And for this part, it will select the leader to propose a block to the whole network. And the public key of this leader will be revealed to all the people, and they will be able to verify that these people actually draw the lottery to become the leader. So the leader is selected through the verify function. It is selected randomly and selected secretly. And after it shows the identity to all of other nodes, the leader can propose a new block to whole network to let them know that this is a new block we need to be to do our consensus process on, and we can either agree on this block at the end of the day, or we can either reject it. And so this is the first step. And the second step is a little bit similar, that we're still going to run through another VRF round. We need to randomly select 1,000 tokens to form a small committee. And this committee will decide that if we want to accept this block proposed by this leader, or we want to reject it. And they will run a very concise consensus process, which is also quorum based, and they will try to reach agreement on the proposed block. So as you can see here, the secret behind Algorand is that on the final step here, we are still running a pretty classic consensus algorithm, a quorum based that supports I suggested here that supports less than 100 nodes, but this is for the last round. If you have, but in the overall consensus mechanism, you can have limitless of numbers of nodes joining the network, and just but for each round of the consensus, each node will go through these two mechanisms. So first, you need to have a number of nodes to have the right to be selected as a leader, and then it needs to be selected as a committee to handle the consensus. So these two processes make sure that all of this, all the nodes are decentralized. The distributed nodes are decentralized, and they all have power to join the consensus. But in the actual consensus process, only a small number of nodes can join, and they have and these nodes will have the stake on their hands, and they have incentive to be not be Byzantine. Yes, that's possible. If there's a very rich people, they want to buy all of the maybe not all of them, maybe half of the Algorand tokens, then they will have half of the right to participate in the consensus. But considering the fact that they have spent a lot of wealth on purchasing these tokens, so they are incentivized to not make this token worthless, right? So if you attack this network, so when we are talking about attack, we're actually talking about two things. The first thing is attack cost, which is how much money you need to spend on making this attack. And the second thing is attack benefit, which is how much money you can make from this attack. So attack can only happens when the attack cost is much lower than the attack benefit. So if there's any case that, so this is, I'm talking about this in a pretty academic basis. So this is how we consider problems in economics, and we consider attack cost and attack benefit. What we want to do is to design a mechanism that makes the attack benefit is much lower than the attack cost, so that the attacker has no incentive to do it. Does the leader have to have certain computer capability to propose a new block? Actually not. To propose a new block, you just need to collect all the transactions that you have received from the client or from other nodes and pack that into a single block. And then you just need to verify all the transactions in it. And this is usually very fast. You just need to just run the software to verify each of the transaction based on the current state of the blockchain to make sure that there's no double span, there's no overspan of any account. And if all the transactions are valid, you just pack them into a block and then broadcast it to all of other community nodes. Yes, VRF doesn't consider whether you are rich, but that is exactly why we need to have this proof of node permission mechanism here. We need to make sure that just through this mechanism, one token stands for one piece of voting power. So if you have more tokens, then you have more voting power. But if you have more tokens, you have more stakes, then you are less likely to jeopardize the whole system. As failing the system, whole system fail will make your stake worthless. So you have this incentive in it. Larger than more nodes with more tokens, more chances. Yes, if you have more tokens, then you have more chances to participate in the mechanism, in the consensus. That's how it works, basically. Okay, then here's let me just quickly walk through how this works in detail, in a pretty figurative way. So the first thing, each of the node here, the first thing you need to do is in your local computer, you run a lottery, and you can know that if you are selected in this round if you are selected, then you should propagate a message to the network, and this contains a lottery of yours and your public key, so the other knows that you are actually verified. You actually draw the lottery, and these are all powered by the cryptographic tool called VRF. And the second step is that they will all of the nodes will just communicate with each other to verify the VRF proof, so here not just one node will be selected. So here we will have multiple nodes be selected to be the leader of this round. So you can see here we have multiple nodes, and they all have selected. But at the end of the day, there will only be one block be proposed to the whole network to run the consensus algorithm on. And to do that, we are going to do this on the basis that we choose the lowest block proposal. So the lowest proposal means that we will have for each of the block proposed by each of the nodes who has gone through the VRF process, they will have a VRF proof, and this is actually a hash. So we will choose the lowest hash of them all to accept his block as a final block to be proposed to the network. So this is a process we call it soft vote part 1, and this is the block proposal part. Transaction in answer. Okay, let me take this question afterwards. Let me just finish this first. And the second is the part 2 of the soft vote is to still run another round of VRF, to draw another round lottery to select a number of nodes to participate in the community, and they will do the consensus algorithm based on the block proposed earlier, and this will continue for 2 rounds to reach the quorum for 2 rounds and to finalize the consensus. So here it's proposed it 1 time, and here it just voted for twice. And after this, the block is either accepted or rejected, and the consensus is completed. A VRF take it could be very fast, but it depends on your computation specific on your computer specifications. Usually it takes, I think, less than of course less than a second, but I'm thinking about maybe 500 microseconds to 700 microseconds. That's what I'm thinking. but it actually depends on your computer specifications. So in conclusion, we have Algorand that has no fork, because we have the property of the quorum-based consensus algorithm, and it also has very fast transaction finality. And also we can accept a limitless number of nodes to participate in the network, because that we have all of these three mechanisms that make sure that even though there's a bunch of nodes here, but when they go through this whole process, at the end of the day, there will only be a number of selected nodes to participate in the consensus process each round. So we can accept limitless of number of nodes, which also makes our network permissionless. And another property I want to mention here is partition resilient. This is actually also a major problem. How about the selection process after VRF? Let me finish this partition resilient. So sometimes it happens that maybe multiple of the computers in the network are offline, and when they are trying to reconnect to the blockchain network, and they are somehow missing information from the network, and to quickly help them to get back to the synchronized status, and we provide a partition resilient feature that help this offline nodes to quickly get back to unsynchronized with all the other nodes. How about the selection process after VRF? Let's say in this part, the VRF is basically running lottery, and each node will know if he or she draw the lottery, and the accounts, the node that is selected will know that it is selected, and they just propose a message to the network to tell other people that, oh, hey, say I draw the lottery, and here's my proof. And other nodes will verify that this is true, that this node this account is actually indeed selected. And there will be multiple nodes like this. We will select multiple nodes in this round, but we will only accept one block proposed by one of them. And we will do this on the basis of the lowest block, which is based on the VRF proof they propose, which is the hash. So the smallest number of hash of the block accompanied with the block will be the lowest block, and which will be the final block proposal that is propagated to all of the nodes in the blockchain. And then the second round of VRF is to choose a committee. Still, as a node, you will know that if you are chosen as one of the committee node, and then you can just run through the consensus process to agree on the proposed node or reject it. And you need to do this twice, as you need to vote it for twice to reach the quorum. So this is the process. Okay, so enough about the consensus algorithm, and I think we are ready to jump on the coding. And we will have like a 10 minutes session break, and we will get back on 10:50. But before that, let me just do a quick shout out to benefits to you guys, that if you want to earn some algo rewards, here are some things you can participate. So we have a developer ambassador program, which basically, let me just click into it. And also we have grants program, and also we have an Asia acceleration program. So the developer ambassador program basically means that if you contribute to our ecosystem, our community, through maybe creating a solution has a code sample text, then you can get 5,000 algos, or you can create some tutorials, you also get some algos. And you're also welcome to make videos along it. You will get 1,000 algos extra. And also we have a grant program which offers you, depending on what kind of contribution, what kind of application you want to build. Like if you want to build a research project, you want to do an infrastructure development tools, or you want to build an application, build use cases, or you want to do a educational program to our community, you can apply to our grant program according to these two different categories. You can just click into it and grant opportunity. And at the end, you can see that you can either apply to our grants funding, you can apply to our development awards, or you can apply to our developer ambassador program. And also we have an Allground Azure Accelerator program. So this is a joint program between Allground and Longhash. This will happen in Singapore. And for the finalist we choose for this program, we will give you 15K USD dollars as a front up reward, and which will support you to finish your project. And after you accomplish your project, we will also award you with some tokens, some financial support. We will give you give you access to some of the investors. You have opportunity to demo your project to them, to get funds, and also you will get suggestions from all of them. So here are some of the mentors you will meet. So it's a great program. It's kind of like the Y Combinator of blockchain, but specifically this one is specifically for blockchain. And we will give you enough funds to support your project. And if you are interested, then just click here and to apply. Okay, now for this, regarding the slides, I will send it out after the webinar. So please join our Telegram channel. So I will copy and paste our channel. Sorry, just give me a minute. Yeah, please join our Telegram channel. I will copy and paste the link into the into the chat box. So if you are interested, then just join it. I will share my stats later in here. Okay, let's have a 10 minutes break, and I will be back in 10 minutes. Okay, see you later. Also, just feel free to shoot any questions in the chat box if you have any. I will answer them when I come back. Project named Coaching, and Coaching will be the permissioned version of Allground. It will be a blockchain framework that you can use to build your own blockchain. And this Coaching will has all the features of Allground, and it will have the same developer experience as Allground, but you can deploy that into a permissioned version of Allground. And we actually, in the use case I mentioned before, the collaboration between Allground and the Marshall Island, the country in the Pacific Ocean, the small country, they are going to issue their national digital currency, and that currency will actually be based on the Coaching framework. So if you want to have a permission version blockchain to build your application, you can use this Coaching. But the Coaching is actually still under development, and it will come out late this year, maybe at the end of this year or early next year. So you will be able to do that. Yes. If I have another question is, if I have this Allground token purchase, can I make a separate token, like for example in asset block project? Oh, sorry, this is a question I missed before. Thank you. Can I have on for transaction and another for one for transaction, another for dividends without the voting function? Actually, yes, you can do this with our smart contract functionality, and you will be able to issue tokens based on our ASA standard, Allground standard asset standard, and you can design that token into a dividends token that without the voting function. Yes. Is the remaining part of the workshop just a demo, or we can have the instructions so that we can follow? I will try to make this into a session that you guys can all follow. Oh, maybe. Okay, let's start this session. So first thing I will do is that I will